Hello, it's Christian, the CTF noob again, and today we're going to have a look at the 7th behemoth challenge from OverTheWire. This time we have to write our own shellcode, but we'll use pawn tools to support us. So let's get started with behemoth6. Of course we start by connecting to the challenge server via SSH, and then inspect the provided challenge files. For the first time in the behemoth series we have two files to work with. Because we have to start with something, let's run behemoth6. The program simply responds with the message incorrect output. Maybe if we run behemoth6 reader, things get clearer. When running the behemoth6 reader, the program simply responds with the message couldn't open shellcode.txt. Now we know that the reader tries to open a file. We could create a temp directory, create the shellcode file there, and then run the program again. But before we do that, it makes sense to use ltrace to maybe figure out what the programs are doing under the hood. When running behemoth6 with ltrace, we can see that it starts at libc start main and then calls the behemoth6 reader with popen. The man page of popen states that the popen function opens a process by creating a pipe, forking and invoking the shell. Since a pipe is by definition unidirectional, the type argument may specify only reading or writing, not both. The resulting stream is correspondingly read-only or write-only. So popen is used to call the behemoth6 reader and reads its output. Afterwards, malloc is called to allocate memory and fread is used to read from the previously opened stream. After that, pclose is called to close the file stream. Now string compare is called to compare the string couldn't O to Hello Kitty. That's interesting. We know that the behemoth6 reader currently outputs the string couldn't open shellcode.txt. So behemoth6 runs the behemoth6 reader and expects its output to be Hello Kitty. Since this is currently not the case, puts is used to output the message incorrect output. So we know that we have to make the behemoth6 reader output the string Hello Kitty. But what does the behemoth6 reader exactly do? To find this out, we run the behemoth6 reader with ltrace too. Again, the program starts at libc start main. Then it calls fopen to open the file shellcode.txt and uses puts to output the message that shellcode.txt couldn't be opened. So now we have to create the file shellcode.txt and see what the program does with that file. For this, we create a new temp directory. We change then into the new directory and in there create an empty file called shellcode.txt. So let's run the reader again with ltrace and see what changed. This time, opening the shellcode file doesn't fail. fseek, ftell and rewind are called. Then malloc is used to allocate 0 bytes of memory, probably because the file is currently empty. Then fread is used to read the non-existing contents of the file. And finally, fclose is called to close the file stream. Now we can see that the program segfaults. I guess we have to give the reader some file contents to work with. So I enter some capital A's into the shellcode file and then open the reader in GDB. As always, I set the disassembly flavor to Intel and then disassemble the main function. In the main function, we can see the call to fopen and then at main plus 45, the jump not equals to main plus 68. This redirects execution to main plus 68 if the file could be opened. Down there, we can see the first call to fseek, then the call to ftell, and then rewind. Now at main plus 124, malloc is used to allocate memory for the file contents, which are copied with fread, and then the file stream is closed with fclose. Okay, so far we already knew what would happen because we saw all that with ltrace. Now at main plus 176, there is an unconditional jump to main plus 223. There we can see that EAX is called. Probably the contents of shellcode.txt are interpreted as shellcode. To confirm this hypothesis, I create a breakpoint at main plus 240 and then run the reader. At the breakpoint, we can then inspect what's at EAX. We can see a couple of 41s, which are the 4 A's which I entered in the shellcode file. So indeed the contents of the shellcode.txt are interpreted as shellcode and simply executed by the behemoth6 reader. We know that we have to find a way to create a shellcode that outputs the string Hello Kitty. After a little bit of searching the web, I found Shellcraft as part of the pawn tools. Shellcraft provides shellcode snippets for multiple purposes. Using the L parameter, we can list shellcodes that can be used to echo out strings. We find i386 Linux echo, which seems to be exactly what we need, so let's try it out. Shellcraft created a shellcode that we can use, so we have to save it in the shellcode.txt file. Just so we know what exactly the shellcode is doing, we can have a look at the assembly what that Shellcraft can provide too. The command states that Hello Kitty is pushed to the stack. The hex value 1010101 is pushed but isn't in the ASCII range, but it is XORed against hex 1017875. We can use printf and a bash arithmetic expression to XOR the two values ourselves. The resulting bytes, hex 79 and hex 74, are in the ASCII range and are the letter Y and T, so the last two characters of the string Hello Kitty. The following two pushes to the stack are just the remaining characters. Then, as the command states, the write syscall is prepared and then triggered with the interrupt 80 at the very end of the shellcode. I had a more detailed look at interrupts and Linux syscalls in my video on the Narnia 1 challenge. If you haven't seen it already, I linked it in the video description. Now, the shellcode is pretty easy to understand, and it wouldn't have been hard to write it ourselves, but the tool support made things easier and quicker, so it makes sense to automate such tedious tasks. We just have to make sure that we understand what is generated and how it works. So let's finally run the behemoth6 reader. The reader outputs the string Hello Kitty, but it never stops. Of course, that makes sense, since exit is never called to properly exit the program. Maybe there is something useful in the Shellcraft templates. So we search for a shellcode that contains the string exit in its name, and we find i386 Linux syscalls exit, which sounds promising. Let's have a quick look at its assembly. It simply zeroes out EBX and calls the exit syscall, so it's exactly what we need. Let's append it to the shellcode.txt file and run the reader again. The string is printed correctly and the program exits properly. So let's run behemoth6, which prints incorrect output, but why? Let's analyze this with ltrace. The strings match and the correct message is printed, and then we get a shell. Maybe it's something with permissions. Let's try this out and give full permissions to everybody on our temp directory. Now we can run behemoth6 again. The correct message is printed and we have a shell. Perfect. So let's check who we are with who am I. And since we are behemoth7, read the password file for the next stage. So we solved the challenge and are done with behemoth6. Once again, I hope that you found this video interesting. This time we had a little bit more to analyze, but in the end the solution was pretty simple. If you liked the video, please give it a thumbs up. And if you want to see me solving more CTF and wargame related challenges, please subscribe to my channel and don't forget to press the bell icon. If you have any questions, feedback or other challenges I should have a look at, feel free to leave a comment under the video. Thank you and until next time.